So we're continuing now with the G proof, our rigorous mathematical proof that God exists based on first-order predicate logic and 5 axioms no scientist can reasonably deny. This is video 3 out of our 9 videos, and we have a website at thegproof.org. I'm Mark Lawrence Donald Emerson, and I'm your teacher. What we're doing in this video is called Sentential Logic, and it was developed by a number of people on this list here. So, as I said, this is video 3. This is a crash course in Sentential Logic. Here's a map of all of our videos. The cyan color means we've already been there and finished that, so we finished with videos 1 and 2. And now we're at video 3 right here, in the midst of all the ones on the left side of the slider where I'm teaching you logic. And after this we'll go on to video 4 and video 5 where I will teach you about predicate logic. We'll use all this in videos 6, 7, and 8 where I'm going to show you the proof. First in video 6 and also in video 7 I will present all the theory that we need to understand the proof, including our axioms. And then in video 8 we'll do our formal rigorous proofs that God exists. And then finally in video 9 we'll talk about the consequences. Alright, so this is video 3, Crash Course in Sentential Logic, and here's an outline of this video. First we'll talk about letters and symbols, and then in these sections here I'm going to present 9 rules of logic to you, and we're going to do 3 example proofs. And then we'll use all these rules and these proof techniques when we get to videos 4 and 5. Okay, now I want to talk for a minute about information overload. This is a crash course. I'm going to cover a lot of information in this video. It all makes very good sense like the geometry did, but this material is a little more advanced than what we did in video 2. So, if you don't understand something I said, please back up the video and watch it again, maybe more than once, until you get it. Also, if you are understanding everything but you reach a point where your mind is just like, well, I'm getting overloaded, this is too much, stop. Take a break. Give your mind a rest. The mind needs time to integrate and learn, and that includes rest time. And then resume later, maybe an hour later, next day, 2 days later. Different people learn at different rates. It also depends on how much you already know about this stuff. If this is brand new to you, there's a lot more to absorb. Now the first few times that I teach a new concept, I go slowly. But then as I use that concept over and over, I go faster because I expect you to know it and I need to save time. I only have an hour to get through these videos. Alright, so here we are in video 3. Now we're going to dive in and look at our letters and symbols. Letters and symbols. Here we are on the outline up here. Now, we're going to use 3 letters in sentential logic. Capital P, capital Q, and capital R. And each letter means a whole sentence. We get to make up the sentences. We're not going to use any other capital letters, and we're not going to use any lowercase letters at all till we get to video 4. Here's an example. P might mean Sarah has long hair. Q might mean Nathan loves Sarah. R might mean Sarah eats chocolate. Here's another example. P might mean liberty is more important than safety. I think that's true. Some people might not. Q. All politicians are honest. Well, don't you think that's true? R means 3 plus 4 equals 7. That's for sure true. All right. Now we have some restrictions on the letters. We're using declarative sentences only. A declarative sentence has the property of being either true or false. It might be unclear whether it's a true or false, like a couple of the ones I just mentioned, but it has the grammar structure of truth or falseness, you see, in contrast with these other ones. Now look, no interrogatory sentences. These are questions like, does Sarah love Nathan? That is a question. We're not doing those. Why does it matter whether God exists? That's it. We're not covering that in logic. Also, no exclamatory sentences like whoops or oh my God with exclamation point. We're not doing those. No imperative sentences. These are commands like be nice to your little sister. Or vote yes. These are sentences, but they don't have the property of being true or false. They're just commanding something. Also, no sentence fragments. Like chocolate, that's not a sentence. Sarah's long dog hair, that's not a sentence. We will deal with fragments when we get to video 4. All right. Now, we're going to talk about 5 symbols here. What we will do is with sentences like P and Q, we will put them, smaller sentences, together to make bigger sentences using these 5 symbols. This is not, this one means not, this one means and is this way, this one means or is that way, it's upside down from and. This one means if then, it's 2 lines with an arrow pointing to the right, and this one means if and only if, it's the same 2 lines with arrows pointing both ways. Now we'll go over all of these. Not. Okay, let's suppose that the sentence P means Sarah has long hair. All right, what does this mean? It means not P. It means Sarah does not have long hair. Very easy. And a sentence of this form is called a negation. And, that's the one that goes like this. Okay, we'll add another sentence here for Q. Nathan loves Sarah. Okay, this sentence means P and Q. Okay, P and Q. Sarah has long hair and Nathan loves her. How about this sentence? P and not Q. This means Sarah has long hair and Nathan does not love her. Now, a sentence of this form with the and is called a conjunction. Here's or. Or, we flip the sign upside down for or. We're going to add a third sentence here, which is or. Sarah eats chocolate. Now, what does this one mean? This says P or Q. In other words, Sarah has long hair or Nathan loves her. Here's another example. A little bit more complicated now. Look at this one. I'm just going to read the letters first. Not P or Q and R. Now, here's how I could say this in English. Sarah does not have long hair or Nathan loves her and she eats chocolate. Now, there is an issue here about the parentheses and what that means. We'll talk about that in a few minutes. Now, a sentence that is of this form with the or is called a disjunction. Now, we'll talk about if-then. This symbol here with the arrow pointing to the right, only to the right, not to the left, means if-then. It also means implies. We have 2 different ways of saying it. So using the same sentences here, this sentence right here says, if P, then Q. See that? If P, then Q. If Sarah has long hair, then Nathan loves her. But we have another way of saying this that's a little bit easier to say, and that is, Sarah has long hair implies Nathan loves her. Now, when we use the word implies in logic, and actually in all of mathematics, we mean it in this very strict sense here. Sometimes it's used in a casual conversation, oh, he had an implied meaning, like it was between the lines or something that something secret or something that's not stated. That's not what we don't mean it in that way when we use the word implies in logic. We simply mean if then. Here's another one. If R, then not Q. We could also say R implies not Q. What does this mean? If Sarah eats chocolate, then Nathan does not love her. See, because R means Sarah eats chocolate, and Q is Nathan loves her, or not loves her now in this case, okay? A sentence of this form, with the implies sign, is called a conditional. Now, when is a conditional true? Let's look at these 2 sentences. Let's let P mean Natalie lives in California, and Q mean Natalie lives in the United States. All right, P implies Q. This means if Natalie lives in California, then she lives in the United States. Well, you know what? That is true. It doesn't matter who Natalie is. It doesn't matter where she lives in California, because the totality of California is inside the United States. So wherever she's in California, she's guaranteed to be in the United States. Okay? So it's true. It also means that the following is true. Look at this. What I've done here is I've taken the P and Q and I've switched them around and I put not signs in front of both of them now. Look what this says. Now think about this. If Natalie does not live in the United States, then she does not live in California. You see that? What if she lives in France or China? Well, she doesn't live in California, because if she's not in the United States, she can't be in California. Okay? All right, now, so what I did was I took the conditional, I took the if-then statement, and I switched it around and I put nots in front of both of them. What if I switch it around without putting nots in front of both of them, like this? I just switch it around and make Q implies P like this. What does this say? If Natalie lives in the United States, then she lives in California. Well, that is false. It is not true. She might live in Nevada or Texas. You can't say if she lives in California, then in the United States, then she lives in California. That's not guaranteed at all. This sentence is false. All right. Now, the last one, if and only if. This sentence, if I say P, if and only if Q, means both of these are true. It means the forward conditional is true and the backwards conditional true. It means P implies Q is true and Q implies P is true. Okay? So now, let's use these two sentences. So this P if and only if Q means now with these sentences, Sarah has long hair if and only if Nathan loves her. Now that means we get both conditionals. It means we get if she has long hair, then he loves her, and we also get if he loves her, then she has long hair. See that? And so this is called a biconditional because it's a conditional in both directions. All right, I'm going to talk about something called logical equivalence now. Let's look at these two sentences. Let's P means Charles is in the 14th U.S. state. And Q means Charles is in Vermont. Well, you know what? The United States started as 13 states, and then the rest of the states got added one by one. Well, it just so happens that the first new one, in other words, the 14th one, was Vermont. Okay, so this sentence here, P if and only if Q, what does that say? Charles is in the 14th state if and only if he's in Vermont. This is true. Let's see why. Well, I know if I have P if and only if Q, then I get both conditionals. I mean that I get that P implies Q. If he's in the 14th state, then he's in Vermont. I also get, remember if I turn it around with the not signs, if he's not in Vermont, then he's not in the 14th state. I get that's true too. Also, I get to switch the conditional around. I get it the other way because this is a biconditional, which means if he's in Vermont, then he's in the 14th state. And if I turn that around with the nots, if he's not in the 14th state, he's not in Vermont. He's totally boxed in. He's either in Vermont and he's in the 14th state, or he's out of Vermont and he's out of the 14th state. Because being in the 14th state is logically equivalent to being in Vermont. You're either in Vermont or you're not. You're either in the 14th state or you're not. And if you're in, they're the same. In other words, when P if and only if Q is true, it means that P and Q are logically equivalent. Okay. Let's talk about parentheses and nesting and what is the outermost statement. I'm going to use my little pointer here. Okay, let's look at this sentence right here. Okay, it says P if and only if Q, that's in parentheses, implies P and R, and that's also in parentheses. Now, what are the building blocks here? Well, the things in parentheses are nested things. So this thing over here, this P if and only if Q, that's nested. And then the thing on the right, P and R, that's also nested. Okay, so what is the outermost statement? The outermost statement is what I get by putting those two together with the if-then. It's if that left thing in parentheses, then the right thing in parentheses. So it's implication side. The left parentheses implies the right parentheses. So that's the outermost statement right there. That means the outermost statement is a conditional. Okay? Which is why I made the conditional sign pink here. All right. How about this one? I have P if and only if something in parentheses. Q implies R is in parentheses. It's nested. It's the right-hand side of this biconditional here. Okay? And so what, and the thing in the P is all by itself. The outermost statement here has to be the if and only if, the biconditional, right? So the outermost statement is a biconditional. That's why I made it pink up there, okay? How about this one? We've got some parentheses over here. P implies Q. That's in parentheses. And then and R. Okay, what's the outermost thing? Well, the parentheses are never the outermost thing. The outermost thing is the and. It's the parentheses and the R. So that means the outermost statement is a conjunction. You see that? Okay. So that takes care of our discussion of letters and symbols. That's why I've made this cyan. And so now let's move on. We're going to go through the logic rules and the example proofs, and I'll show you how we're going to do that. Okay, first we're going to start with working with conditionals. As I go through the outline here, we're going to talk about, now in detail, we're going to talk about conditionals and conjunctions and biconditionals. We're going to drop the negations and the disjunctions because we don't need them in our proof that God exists in version 1. If you go to the version 2 technical paper, we will definitely need them there. But I'm going to drop the discussion now of not and of or. Okay, so we're going to begin with conditionals, and we're going to begin with our first rule, which is called modus ponens. Okay, modus ponens is Latin, and don't worry, I did not make that up. That's from logic. All right, let's look at these two example sentences here. P means Cindy studies hard for her logic class, and Q means Cindy gets an A in logic. Now let's suppose that we know these two things. We know if Cindy studies hard for her logic class, then she gets an A in logic. And we also know Cindy studies hard for her logic class. What does that mean? That means we can infer this. It means she gets the A, right? If we know that if she studies hard, she gets the A, and we know that she did study hard, that means we can infer, yeah, she got the A. And this is by the rule of modus ponens. Let's put this in letters now. In other words, suppose we know if P, then Q, and we know P, then we can infer Q. Does that make sense? By modus ponens. And here's how we put the rule in our, the way it will appear in our proofs. So I have up here, I have this statement up here. This is pink implies blue. See, there's the implication sign between, I have a pink statement implies a blue statement. If I know that, and I have the pink statement, then you see there's two arrows here, then I get the blue statement by the rule of modus ponens. And since there are two arrows, we know there have to be two items in the from column. Okay, so we're going to use that now. Okay, so let's move on and do our next rule, which is repetition. So we already did this. We did repetition in geometry, remember? We use it to copy something that we already have. Just copy it down again, like givens. And these other things we'll copy down in with this rule in video 8. Here's the rule. You've already seen it. If I have the pink statement, I can write it down again. Very easy. Next rule, stating a claim. This is the claim rule. Claim rule can be used to write any statement we want in the middle of a proof. I can write any statement with one little catch, big catch actually. I have to put the word prove in front of it. And there's another catch. I can't use that statement later in the proof until the word prove gets canceled out. And there are 4 different ways to cancel out the word proof. 2 of them I'm going to teach you in this video, conditional proof and direct proof. And in video 4 I'll teach you universal proof. And the last one, indirect proof, I'm not going to teach you in these videos because we won't need it in video 8. So, but it will be needed in version 2 of the theory if you read the technical paper. Now, line 1 of every proof is always a claim. I'll show you that in just a moment. And the claim rule is easy to use, but sometimes it's hard to figure out what statement to claim. Here's the rule. I have this yellow statement. I can just write it. I can write the yellow statement. It's any statement I want, but I have to put the word prove in front of it, see? And I cannot use that yellow statement until the word prove is canceled out. All right, now, rule 4, conditional proof. This is a rule that we use to cancel out the word prove. All right, but first let's talk about what we need to do to prove a conditional. Now, let's talk about a couple of sentences here. Let's let P be baking soda is mixed with vinegar, and Q means the mixture fizzes up. Now, look at this red sentence here. This red sentence says, if baking soda is mixed with vinegar, then the mixture fizzes up. Now, how can we test to see if this sentence is true? What do we need to do to find out if that's true? Well, I'll tell you what we need to do. We need to go in the kitchen and try mixing some baking soda and vinegar and see what happens. So I mix the baking soda and vinegar, now what? What if it fizzes up? If it fizzes up, then this red statement is true. You see that? How can we test whether this red sentence is true? This red sentence says, if P, then Q. Is that true or not? How can we test that? Well, here's how we do it. We try P. Okay, let's see. Let's assume P is true. Let's take that and see that if we can get Q based on P, then it's true. see that? Just like the baking soda and vinegar. Now, when we're doing the baking soda and vinegar, what if we don't? What if we don't go in the kitchen? What if we don't bother mixing baking soda and vinegar? In other words, let's say the sentence P up here is false. Baking soda is mixed with vinegar, false, we didn't do it. What does that mean? It's irrelevant. For the test, we don't care about its false. We only care about if it's true. You don't have to try not mixing baking soda and vinegar to find out if this red sentence is true. Okay? So, Rule 4, conditional proof, which has two parts, ACP and CP, which I'll show you in a second. Suppose we want to prove if P, then Q. In other words, we want to prove P implies Q. Well, how do we do it? We start by assuming that P is true. In other words, we try P. Now, we don't know that P is true, just like we don't know that we mixed baking soda and vinegar. We might not have, okay? But we assume it is. That's called our assumption for conditional proof, ACP. And then, after that, we try to get Q in our proof. It might be easy, it might be hard, it might be impossible. If it's possible, then the proof isn't going to work. But if we manage to get Q, then we have proven P implies Q. And how? By conditional proof. Now watch how this works. I'm going to put the rule up now. I'm just going to go through a sequence on this rule so you see in my abstract example here, and then I'll make it concrete in our example proof in just a moment. So here we have, we're in the middle of a proof, and we have written a line here that says the word prove, and then it says pink, and then see there's the imply sign, blue. So prove if pink, then blue. See that? And that was by the claim rule. We'll do this in the proof in just a minute. Now, if we have a claim line like this, where it's a conditional, where it says pink implies blue, then the next line, the very next line after the claim, then we can write the pink. In other words, we're going to assume the pink. And then we're going to do some, and by the way, that's by ACP. And then we're going to do some work in our proof. And if we manage to get the blue, that means we're done with that proof. So we can write the word done, and the reason is CP, conditional proof. And when we get the word done, that gives us the right to put a box around these lines here. And I'll explain this, just I'm being very abstract, just bear with me and see what happens. I'll put this all in practice in just a minute, then you'll understand it better. And after we write the box, then we get to cancel the word prove out. And when the word prove is canceled out, that means that line up there now can be used later in the proof. Okay. So, we're ready to do our first example proof. And here it is. We have a given and we have a prove. We're given that Q implies R. We have to prove that if P implies Q, then P implies R. All right? And we have no diagram. Okay? No diagrams in logic proofs. So we're going to use 4 columns, just like in geometry proofs: the line number, the statement, the from, and the by. Now, we're going to begin by using the claim rule, which says if I write the word prove first, I can put anything I want, and here's what I'm going to put in line 1. I'm going to write prove this yellow thing, which is what this yellow down here is. Okay? And this is from, well, it's by the claim rule, see? And I don't have to put anything in the from rule because there's no arrow in the claim rule. And by the way, as you can see, I'm using color here. I'm going to use a lot of color when we're doing proofs now to show you what's connected to what. All right, now why did I pick that thing, this yellow? Look at it. Look at that. It's exactly the same as what I'm trying to prove, see? The 2 yellow things are exactly the same. And that means if I'm able to prove this, then I'm done. That's the reason I put that as line 1. Okay, and by the way, I will take the colors away. I use the colors to show you some connections, and then I take them away, and then I use them again. And each time I use the colors, I use them a little differently. Okay? All right, so now how are we going to do this? Well, we need to take a good look at line 1. Line 1, what is the outermost statement here? Well, we've got this pink thing in parentheses, and we've got this blue thing in parentheses, and we got a conditional between them. So it's a conditional. It's if pink, then blue. Okay, or pink implies blue. That's the form of this statement here. Well, if we're trying to prove a conditional, then we can use our rule of conditional proof. If we can try to use it, let's see. Okay, so if we have a prove line like this, then we can, the very next line, we're allowed to assume the pink. We're trying to prove pink implies blue, so we assume the pink. So that's what I'm going to put in line number 2. So the pink says P implies Q, and so I'll put P implies Q down in line 2. See that? All right. This is our assumption. So in the by column, I write ACP, which means, it's just like I did here in the rule, it means assumption for conditional proof. Now the assumption for conditional proof, I don't use arrows on the proof rules, and so we just have to know that you don't have to put anything in the from column on ACP. And remember, that's because we're assuming that, and now we're going to try to get the blue. So we're assuming the pink, and we're going to try to get the blue now. We'll come back, if we get it, we'll come back to this rule again. And one other thing, notice how the pink, that P implies, in line 2, I have pushed the indentation in one level. See that? It's indented in line 2, okay? Very important. All right. Now, what next? Well, I'm going to use the claim rule again. I already have one proof going. It's pending. It's not done because it's not done until the word prove gets canceled out. I'm going to start another proof inside that proof. See, we didn't do that in geometry. In logic, we can have proofs nested inside of proofs, nested inside of proofs. Okay? So that's what I'm going to do. I'm going to make a nested, I'm going to start a nested proof now in line 3 like this. I'm going to write prove this yellow thing. Now the yellow is something different than it was earlier, because remember, as I use these colors, it keeps changing what they are. Every time I am using the colors, it's something different. Then I take them away. All right. Now how can I write, what is the reason? Well, it's by the claim rule. I don't have to put anything in the from column, so I can prove anything I want. But why did I pick that yellow thing? I'm trying to prove P implies R. Why did I pick that? I'll tell you why I picked it. Look up here. It's exactly the thing that I'm trying to get in the outer proof. In the outer proof, I'm trying to get the thing that's on the right-hand side of that middle conditional symbol there, see? I'm trying to get that. And so if I'm able to cancel out the word prove on line 3, I will have finished the proof in line 1, see? That's the strategy. Okay, so now what? Now let's take a look at this line 3. What kind of a statement is it? Well, I'll tell you what, it's another conditional. It says P implies R. Pink implies blue. Well, to prove that pink implies blue, what do? We use conditional proof. Okay? It says, once again, if I'm trying to prove pink implies blue, I assume pink and try to get blue. Well, that's what we're going to do. We're going to assume the pink. And what's the pink now? Now the pink is that just plain old P, see? P is the pink. So I'm going to write P down in line 4. And look what I did. I pushed the indent level in one more level. It went in another notch, see? Every time after you write the word prove, the very next line has to go in one level. And what is that? That's our assumption for conditional proof, and again, we don't have to put anything in the from column for that. Okay. So now what? Well, I'll tell you what. Look at lines 2 and 4. These lines are both available. They don't have the word prove in them. Lines 1 and 3 are not available because they say prove. You can't use them if they say prove. And it's not until it's canceled. They're not canceled. But look at lines 2 and 4. Now let's look at this rule down here. Modus ponens. Modus ponens says if I have a line that says pink implies blue, if I know that, and I have another line that says pink, then I can get the blue. Remember, we learned about that. Well, look what I have. Line 2, I have pink implies blue, and in line 4, I have pink. See, the pink is the same. P is pink. Right now, the P is pink. All right? That means I can get the blue. I can get the Q. So I'm going to write Q down in line 4. Now, where did that come from? Well, it came from lines 2 and 4 by modus ponens. Modus ponens has 2 arrows in it, which means I have to have 2 entries in the from column. And I do. I have 2 and 4. See how that works? So now this is weaving the way that we learn to weave things together in geometry, just with a new rule. Now what? Well, you know what? I have a given sitting up here I haven't used yet. I'm going to use it now. How do I get the given in there? Repetition. You've learned this in geometry. So I'm going to copy the given in. So this says Q implies R, okay? And that came from the given by repetition, R. Oh, I forgot to mention, I see I put MP for modus ponens. I abbreviate all the reasons because I don't have room to write them out. Okay, now what? Well, look at lines 5 and 6. Now I'm changing the colors around. The colors are doing different things. I'm always changing that. Each time when I put the colors on, they may be something different, but I'm using them to show you what is connected to what. Look at line 5. If I made the Q pink, that's line 5, I have pink. And line 6, I have pink implies blue. Now the Q is the pink and the R is the blue. You see that? That means I can use this rule, modus ponens again. If I have pink implies blue and I have pink, then I can get blue. Well, that's what I have. I have pink implies blue in line 6, and in line 5 I have pink. So I can get the blue. And so I'll put that down here as line 7. And where did that come from? That came from lines 5 and 6, right? By what? By modus ponens, MP. Okay? It's weaving together. But we're not using any star. We don't use stars in logic proofs like we did in geometry. Okay. Now what? Well, take a look at this. R is exactly what we were trying to get in our nested proof. Our inner proof is to try to get R. Okay, see, so what we were doing was we're doing a conditional proof on our inner. Both our inner and our outer proofs are both conditional proofs because that's the only method of proof I've taught you so far. So I'm using it twice in this example 1. When we get to further along, we're going to use different kinds of proofs mixed together in the same one. Okay, so what we did was in line, we were trying to prove in line 3, we were trying to prove pink implies R. And so in line 4, we assumed the pink. And look what we did. We got in line 7, we got the blue. We got it. We got R. And that means that we can use this rule now. Once we have the blue, the next line we write the word done. That means we're done. We're done with the nested proof. Well, almost done. And where did the done line come from? It came from line 7. 7 is where we reached the goal, which was R. So that's why I put 7 down as the from. And what's the by? It's by this rule. CP, conditional proof. Now this rule has 2 things that go. It has ACP and CP. ACP was up here in line 4. That's where I assumed the pink. And then we put CP in line 8 where we're done. Now once we have the done line, now we get to do what we call boxing and then cancel the proof. Before we cancel the proof, we have to do a box. Now look at the indentation level. Lines 4, 5, 6, and 7 are all at the same level of indentation. Those lines, 4 through 8, we now have to draw a box around them. Okay, we're going to put the box now. The box around 4 through 8, like that. Those lines get boxed off, and once the box is around them, then we get to cancel the word prove. So the done line gives us the right to box and cancel. That means that the inner nested proof is done, because prove is now canceled out. Okay? Now one thing you have to know, actually 2 things. Once the lines are inside of a box, you can't touch them. In other words, down here in the proof, I can't use line 5 down here in the proof. Once it's inside the box, it's trapped. You can't use it down below. But now that the proof is canceled out, line 3 is now available. We can use line 3 down here now, and we're going to. All right. Now where do we stand? We have line 3. We got it. Now, we got it kind of upside down because we wrote it. See, what's different than geometry proofs is like we nest in and we do something and we end up with the thing at the top. It becomes then the new thing we have. And so the sequence seems a little odd maybe, but it makes sense because we established line 3 by doing the proof. All right, now look at this. Look at line 3 and the right-hand side of line 1. Line 1 was a conditional proof, remember? We were doing in our outer proof. Let's look back at our outer proof now. It was also a conditional proof, but it was a different conditional. Okay, what we were doing in our outer proof is on line 1, we have pink implies blue, this big pink and this big blue. We're trying to prove that. And we assumed the big pink in line 2. That was our assumption. And we were trying to get the big blue, right? Well, guess what? We just got it. We just got it in line 3, didn't we? That's the big blue. See, it's exactly the same. That means that we have gotten our blue. That means we get to write done. Where does done go? It goes down here in line 9, down here. Now notice that the word done, I have popped the indentation out 1 notch. It's out. Now lines 2, 3, and 9 are all at the same level of indentation, which is out 1 from the ones that are in the box, see? All right? And how do I get the done? I got the done from line 3. Line 3 is where I reached the goal. And by conditional proof. Okay, so conditional proof, there's 2 parts to it. There's the ACP and the CP. The ACP was up here in line 2, where I assumed the pink. And the CP is down here in line 9, where I reference the, or I say done based on line 3, which was the goal. See that? And now that I have done, that gives me the right to box and cancel. What do I box? I box all the things that are at the indent from the prove up here down to the done. Like that. So all of those lines are boxed now. And I get to cancel this prove up here. And that means what we have just done is we have proven line 1. Also, interestingly, all the other stuff is now boxed. It's not accessible. We didn't prove any of the stuff in the boxes. What we proved was line 1 from the given. And there, we're done with our first logic proof. Okay? All right, so the next step now is to work with conjunctions. So here we are in our outline. We're moving on to work with conjunctions now. Let's look at the next logic rule, which is called simplification. Now this rule is very easy. Okay? Let's let P mean Jeannie is smart and Q mean Jeannie is popular. Now supposing we know a conjunction. Supposing we know this sentence right here. Jeannie is smart and Jeannie is popular. Supposing we know that. Well, what can we get? But then we know simplification. We can infer 2 things from that. The first thing we can infer from that is that Jeannie is smart. And the second thing we can infer is that Jeannie is popular. Very easy. In other words, supposing we know P and Q, then by simplification the first way, we can get P. Also, by simplification the second way, we can get Q. We can get the one on the right or the one on the left. Either one we want. What simplification does is it splits apart a conjunction. So let's look at the rule. Here's the rule, and it has 2 different ways, first way and second way. Let's look at the top, what's the first way. It says, if I have a statement that says pink and blue, that's this right here. If I know pink and blue, then I can say pink, right? 1 arrow. Also, I can use it the other way. If I have pink and blue, then I can say blue. And we just put simp, S-I-M-P, either way, whether it's the first way or the second way. Okay? Now let's look at our next rule, which is the opposite, called adjunction. Adjunction, same 2 rules about Jeannie, same 2 statements about Jeannie. Supposing we know 2 things. Supposing we know Jeannie is smart, and we also know Jeannie is popular. Well, that means we can infer that Jeannie is smart and Jeannie is popular, right? This is called adjunction. We're putting the conjunction together. So, supposing we know these 2 things. Supposing we know P, and we also know Q, well, then we can infer P and Q by adjunction. So adjunction puts together our conjunction. All right, here's the rule. We have the pink as 1 line. We have the blue as another line. And then we can infer from that, we can get pink and blue with the and sign in there. And there are 2 arrows, see, because you have to have the pink and the blue as separate lines, and then we get pink and blue as our new line with 2 items in the from column. Okay, so here we are in our outline. Now let's go ahead and do our next example proof. And here it is. So we have a given and a prove. And so we're going to start, we're going to use 4 columns as usual and start with the claim rule. And we're going to write down, prove this yellow thing by the claim rule. Now and what is that yellow thing? That yellow thing is exactly what we're trying to prove here. Now I'm going to bring my pointer out here so we can look at this thing. It's a little bit complicated. What we have here in what we're trying to prove, and it's also in line 1, we have some square brackets here, and inside the square brackets it says P and some stuff in parentheses over here. Okay, and inside those parentheses it says R implies Q. Okay, now looking outside the brackets over on the right hand side it says implies Q. In other words, that whole thing in the brackets implies Q. Alright, that's the thing that we're trying to prove. Well, what does this statement look like that we're trying to prove? Well, like I just said, it's this thing in the brackets implies Q. The outermost statement is this conditional right here. Okay? And so if we're going to prove a conditional, we need to use conditional proof, which means we're trying to prove pink implies blue, so we assume pink and try to get the blue. So we're going to assume the pink. So in line 2, I have simply copied the pink part from up here. You can see it's the part in square brackets. I've copied the pink part accurately there. And this is our assumption for conditional proof. Okay. Now what? Well, if we look at this line 2 here, line 2 says pink and something in parentheses. So the outermost statement there is a conjunction. The thing in parentheses, R implies Q, that's nested. The outermost statement in line 2 is the conjunction right here. Well, that means I can use this rule, simplification, which says if I have pink and blue, then I can have pink. Or I can have blue. Well, I'm going to take blue. Okay? I'm going to take the blue one which says R implies Q, right? That's what's in the parentheses up there. And so where did I get that? I got that from line 2 by this rule here, simplification. The second way. All right. Now what? I'll tell you what. We're going to use the claim rule again, and this time I'm going to write prove R implies P and Q. Oh, where did I get that? Okay, well, first of all, this is by the claim rule. Now, what was my motivation? Why did I want to use that yellow thing? I'll tell you why. Because it's related to the given up here. We're going to use the given a little later, and this is important. This is the left side of the given up here. I'll talk about that some more when we get done with this nested proof. So what I'm doing here is I'm starting a nested proof. Now, I want you to notice again, so far I've been indented. After that first proof line in line 1 where we began the outer proof, I indented. Now we're starting a nested proof, so we have to indent again. The next line we will indent. But first let's talk about what the form of this is. The form of line 4, this is a conditional. It says R implies something in parentheses, this big thing in parentheses, which says P and Q in the parentheses, that blue thing. So if the pink implies this bigger blue thing. How are we going to do that? How do we prove pink implies blue? We use this rule, conditional proof. That's the only kind of proof rule I've given you so far. So anyway, we'll teach you another proof rule after we get done with this proof. So that means to prove this, we assume the pink, right? So we're going to put the pink here in line 5. That's our assumption for conditional proof. So we're trying to prove pink implies blue, so we assume pink. And notice I pushed the indentation level in one more notch. Okay, now what are we going to do? Look at these two lines here, 3 and 5. Both of them are available because I don't have any proof written in either of those lines. That's uncancelled. And I have pink implies blue, and I have pink. Well, this is our friend modus ponens. If I have pink implies blue, and I have pink, then I can have blue. And so that's what I'm going to get. I'm going to get Q. So the pink is the R, and the blue is the Q. I have R implies Q here, which is pink implies blue, and here I have R, that's the pink. Therefore, I can get the blue, which is Q. Where did that come from? Lines 3 and 5 by modus ponens, starting to weave together, just like geometry proofs did. Okay, so now what are we going to do? Well, looking back up here at line 2, remember line 2 is a conjunction. We already peeled off, we already used line 2 one time to get the blue part. I'm going to use this simplification rule again the other way and get the pink. If I know pink and blue, which is what line 2 is, pink and blue, then I can have the pink. And that's what I'm going to do. I'm going to take the pink right here in line 7. Where did that come from? That came from line 2 by simplification. Okay? All right, now what? Well, what I'm going to do now, I'm going to take lines 6 and 7, and I'm going to put them together. And if you look at line 4, you might see why, but I'll explain that in a minute. So I'm going to use this rule, adjunction, which says if I have pink and I have blue, then I can get pink and blue, right? Well, I have Q and I have P. So that means I can say P and Q, right? So here it is, line 8, P and Q. Where did that come from? That came from lines 6 and 7 by adjunction. Make sense? All right. Now look. P and Q, that's exactly what I was trying to get on the right-hand side of this conditional that I'm trying to prove in our nested proof, our inner proof. And so remember, we were doing a conditional proof that we started on line 4. And so what did we do? See, this was a conditional. Line 4, it says pink implies blue, the blue being this bigger thing that's in parentheses. So we started with the pink R, and we tried to get the blue, and bingo, we got it right there. We got P and Q, which is what's in parentheses up here. See that? Okay, and so now that means we're done with this conditional proof here, this nested proof inside. And where did we get that done line? That came from line 8, because 8 is our goal. We reached the goal. See, just like this. See, in the rule here, I have a little I there in the line number. And then I use that I in the from column down here. Because in my rule, just so you can see, I use I because I don't know what number it's going to be. Okay. And so now, since we have our done, that means we get to box and cancel. What are we boxing? See, all of the lines that are indented from this prove in here, I'm going to box those. And then cancel that proof, okay? So now our inner proof is done. Well, now we're going to continue along here, and you know what we're going to do? We're going to use this given now. And we're going to bring the given in using the rule of repetition, but I'm not going to keep writing that rule down. Just like in geometry, I stopped writing it. So here it is. I've copied the given like this. And where did that come from? From given by the rule of repetition. Notice also that when I wrote this line 10, I popped the indentation level out 1. So line 10 is at the same indentation as lines 2, 3, and 4. Because when I cancel a proof, I pop out the indentation level. All right. Now, what does this say in this line 10? Well, it has, I'm going to use my pointer here, it says I've got these things in brackets, square brackets. And inside the square brackets is some stuff that implies R. What's the outermost statement? It's this implication over here. Okay? In fact, let's look at this. We have pink implies blue is the structure of that statement in line 10. But we already proved the pink. Look at the pink up here in line 4. Line 4, what we proved in line 4 is precisely the left side of this conditional in line 10. It's the pink part of line 10. See that? And that means I can use modus ponens. Because I have pink implies blue here, and I have pink here. See that? The pinks match. That means I get the blue, which is R. I get R by, well, where's it from? It's from lines 4 and 10 by modus ponens. Okay? And now what? Well, if we look back at line 3, we already used line 3 once before, but we're going to use it again now. You can use lines multiple times. That's perfectly okay. Line 3 says R implies Q, and look what we have in line 11. We have R. So this says pink implies blue, and this says pink. Well, we can use modus ponens again. You know what? Modus ponens is the rule that we use the most often. So that means I can get the blue, Q, right? So there it is, Q. Where does that come from? Lines 3 and 11 by modus ponens. Okay, Q. Now look what's going on here. Look at our outermost proof. Look at this. We just reached the goal of our outer proof. Our outer proof was a conditional proof. And what did we do? We're trying to prove pink implies blue up here in line 1, where the pink was this big thing in square brackets. We assumed that big thing in square brackets there. That pink thing. And we got the blue. We got the Q, see? That means we're done with the outer proof. We can write the done line now. And where does that come from? It comes from line 12, because 12 is where we reached the goal. On a conditional proof, you put what goes in the from column is where you got the goal. And then CP for conditional proof. Now we get to box and cancel. And what are we boxing? Everything from line 1, below line 1, all the way to the done line, which is all of this, gets boxed off now. And then we get to cancel the proof. And when we cancel the proof on line 1, then we're all done with the proof. We have proved it. We haven't proven anything that's in the box, because that stuff is unavailable. What we have proven is what's line 1, where the proof is canceled. Okay? So that's the end of our second example proof. And so the next thing we're going to do is we're going to work with biconditionals. So let's see where we are on the outline. We've done all this. We've got 6 rules finished here. 1, 2, 3, 4, 5, 6. Now we're going to work with biconditionals. And I'm going to show you 3 more rules, and then we're going to do another proof. Okay. So the next rule is biconditional to conditional, which we abbreviate BC. It's much easier to say BC, which means biconditional to conditional. What BC does, it breaks apart a biconditional into its 2 conditionals. So, supposing we know a biconditional, supposing we know P if and only if Q. Well, that means that we can infer the forward conditional. We can infer P implies Q. And this is by BC the first way. But BC works both ways. We can also infer the backward conditional. Q implies P by BC the second way. Because that's what biconditional is. We said that at the very beginning. What's about biconditionals? Biconditional, P implies Q means you have P implies, it means you have P implies Q and you have Q implies P. And so here's the rule right here. It has 2 parts. It has the first way and the second way. Look carefully up here. On the first way, what's different, look at the green arrows going down. And now, on the top yellow rectangle, it says pink if and only if blue. And then from there we get pink implies blue. See that? And down here, the other way, once again, starting with the same thing. If I have pink if and only if blue, this down here and this up here are identical. Then I can get it the other way. I can get blue implies pink. See? That's the second way that BC works. All right. Rule number 8 is the opposite of this. This is called conditional to biconditional, or CB. What CB does is it puts together a biconditional from its 2 conditionals. So, supposing we know 2 conditionals that are the reverse of each other. We know P implies Q and we know Q implies P. Well, that means that we can infer their biconditional. We can infer P if and only if Q by CB. And here's the rule. If I have 2 things, I have pink implies blue and I have blue implies pink, then I can get pink if and only if blue. 2 arrows means 2 reference lines. Okay, now one more rule, last rule here, rule number 9, which is called direct proof. All right, direct proof is what we did in geometry. It's very easy. Supposing we want to prove P. Well, we just try to get P. That's what we did in geometry. Here's how it works mechanically in the logic proofs. If we have a claim line that says, prove a pink thing, then we do some work until we get the pink thing. If we can get the pink thing, then we're done. We get to write done by DP, which is direct proof, and then we box and cancel the proof, like that. Okay? And so now we're ready to move on to our example proof number 3. And here it is. We have 2 givens now and 1 proof. And as usual, we're going to use 4 columns, and we're going to start with the claim rule, and we're going to put down prove the thing by the claim rule, and we're going to say prove the thing that we're trying to prove. And what is that? It says something in parentheses, if and only if R. Oh, we're trying to, what is that? It's a biconditional in it. The thing in parentheses is nested. So we're trying to prove this biconditional here. How do we prove a biconditional? Well, what we have to do to prove a biconditional is we have to use direct proof. And on the way, we have to do two things. First, we have to prove the forward conditional. See, there's the biconditional. We need to prove the forward conditional and box and cancel that. And then we'll prove the reverse conditional and box and cancel that. You see? So we're going to do it by, like I said, it's going to be a direct proof. And then we're going to use, after we get both of them, then we'll use CB to put together the biconditional, and we'll finish the direct proof. You'll see what I mean if you didn't follow it right there. Okay? So now we're going to bring in given 1 up here. Bring that in by the rule of repetition, given 1. And what does it say? It says Q if and only if R. It's a biconditional. Well, I'm going to let it sit there for a minute, and now I'm going to make another claim. We'll use the claim rule here, and we're going to say prove pink implies blue, and that's by the claim rule. And look what it is. I'm taking line 1. Line 1, I'm trying to prove a biconditional, this pink if and only if blue. And now I'm trying to prove the forward conditional, if P then blue. Okay? See, that's in line 3. And then we'll do, that'll be our first nested proof. We're going to do a second nested proof to prove it the other way. Okay, so we're doing this by, we're trying to prove pink implies blue. We're going to use the conditional proof rule, and so we get to assume the pink and try to get the blue. And this is an assumption by ACP. Going a little faster now. All right, now look at this thing here. This is pink and blue. Okay, P and Q. Well, that's a conjunction, so I can use my rule of simplification to break that apart. And I'm going to take Q. I want Q here. All right, so that comes from line 4 by simplification. Okay. And now what I'm going to do is I'm going to look up here at line 2, which says Q if and only if R. That's a biconditional. I'm going to split it apart using this new rule, biconditional BC, to break it into one of the conditionals. And I can get either way. The one I want is the forward one. So I'm going to take Q implies R. Okay? So that came from line 2 by BC. I split the biconditional into a single conditional going forward. And now look what I got here. I've got pink, and pink implies blue. And so I can use modus ponens, and I can get the blue. I can get the R from that. I got Q implies R, therefore I can get R from lines 5 and 6 by modus ponens. And look at this. R is my goal in this nested proof right here. So I was doing a conditional proof. I'm trying to prove pink implies blue here. I assumed the pink, and I got the blue. So that means I'm done. And why am I done? I'm done from line 7, where I reached the goal, by CP, okay? So now I get to box and cancel. So I box here and cancel here. Now I'm done with the first inner proof. Okay, now I need to do another claim to do the other direction. Now I need to go the other way. This is a claim, and look it up here. See, in line 1, I'm trying to prove pink if and only if blue. I just proved it one direction. Now I'm trying to prove the other way. See, turned it around. The blue implies the pink, see. That's what we're doing in line 2. Okay? And now, I'm changing the colors back so I can use my rule. Okay, so this is a conditional. R implies this blue thing. So I'm going to prove this with the conditional proof. And so as I'm going to assume the pink by ACP and try to get the blue. Well, the blue is a conjunction, isn't it? I have to try to prove P and R. How am I going to do that? Well, I'm going to use this biconditional again up here, and I'm going to split it apart. But I'm going to use, I'm putting this rule up here because I don't have room at the bottom. I'm going to use BC the other way, okay? And split it apart and get R implies Q, okay? Splitting the biconditional apart the other direction. Okay, so that's from line 2 by BC. Okay, and now look at these two lines. I have R implies Q. Well, I can use modus ponens with that to get Q, right? And where does that come from? That comes from lines 10 and 11 by modus ponens. All right, Now what? Well, I have another given up here. P. I'm given P. So let's bring that in. So I'm bringing P in. Where did that come from? That came from given 2 by repetition. Okay? And now, look at these two lines here. I have Q and I have P. Now I can use my rule adjunction to put them together to form a conjunction, you see? So then I can get P and Q. Where does that come from? That comes from lines 12 and 13 by adjunction. Okay, I know the pink, I know the blue, therefore I can get pink and blue. All right. And now look, that's our goal on our second nested proof in here. I'm trying to get P and Q. I'm using conditional proof rule, which I'm sticking up here because I don't have room. And so I'm trying to prove pink implies blue here in line 9. I assumed the pink, that was R, and I just got the blue. Okay, so that's by conditional proof rule. So that means I'm done with that from line 14 where I reached the goal by conditional proof. So now I get to box and cancel. So here's my box, and I cancel my proof. Okay, now I got both of these nested proofs complete. Now what? Well, one of them proves the conditional that I'm after in the forward direction, the other in the reverse direction. So line 3 says pink implies blue, and line 9 says blue implies pink. Well, I have a rule here, which is CB, to go from just that. If I have pink implies blue and I have blue implies pink, then I can get pink if and only if blue. So that's what I'm going to do. Now in line 16, I get this thing here, the pink if and only if the blue. See that? And where does that come from? Lines 3 and 9. Line 3 is here. That was what we proved. The proof is canceled, so we can use it. And line 9, the proof is canceled there, so we can use that one too to get this by this rule, CB. Okay? Now look at that. We just got what we're trying to prove. There it is. P and Q in parentheses, if and only if R. That's our goal. And what kind of proof are we doing? We're doing a direct proof. And in a direct proof, we just try to get it. And if we get it, well, we just got it. If we get it, then we can write done. So we can say done here. And where is that from? That's from line 16, where we reached the goal. And by DP, which is direct proof. So now we get to box and cancel. I'm going to need to get, oh, I'm okay there. So I just did the box. You see, I'm boxing all of this now. See, it's got 2 nested proofs inside. And then we get to cancel that proof up there. And we're done. And so there it is. There's our proof number 3 all finished. And so now we're done. We're done with video 3, our crash course in Sentential Logic. And so I hope to see you again when we get to video 4, our crash course in Predicate Logic Part A, and then on beyond that. Thank you very much for watching. I'm Mark Lawrence Donald Emerson.